What we're going to be going over here is what they refer to as a determinant, and we're going to look at the volume relationship here with this determinant, which really looks at the change in slope here on a function that we're going to be looking at. And this determinant is going to be based on a multivariate determinant. That is, it's sort of a complicated determinant. And we'll look at it from the visual perspective, or at least that's what we'll concentrate on. And our determinant is going to be based on the production function, which is really similar to the Cobb-Douglas production function. Okay, so this is our function we have here. We're going to have a certain revenue output here based on some cost constraints. So the deal is here, we're going to be looking at it in terms of a multivariate calculus problem here, and that we're going to boil that down into a linear optimization, or a linear problem where we can understand it. So we're going to have some revenue output here, a certain amount of revenue per unit for the product we're selling. Just say it's $1,400 times some material and labor inputs here raised to some fractional or exponential amount. So this is where our complexity comes in here, and then we'd subtract from it our budget constraint, and we'd have a certain amount of dollars we can spend here, and then we'd be subtracting the material and labor unit dollars from our revenue. Okay, so what you have to do here when you're setting up this, looking at it in terms of a determinant, you have to come up with a matrix here, and you're going to have some solution points that you're looking at. So we'd set up a Lagrangian equation here, and I'm not going to get into the whole detail here. So we'd add in a Lagrangian here times our cost constraint here, and that would be subtracting here from our revenue output here. So what you would do here, in this case, you just take some partial derivatives of your Lagrangian equation here in terms of labor, material, and the Lagrangian itself. Okay, so that we have here, and then based on those, we're going to have three unknowns, three equations, and we can come up with a solution point, which I'm showing right over here. Okay, and then we'll further expand on this, these first partial derivatives, and we're going to just set up a second partial derivative matrix here. And the only reason for this is really what they call a Hessian matrix, and there'd be some detailing that goes into that. But from our perspective, all we're really interested is looking at this matrix in terms of rows and columns. So we're going to convert this into a linearized vector problem here. But the point is this here. You can see in our matrix here, in our first row, we sort of have a linear. We just got some numbers here. We got a block of numbers on our first row here, and on our second row, our first column, same thing here. But with our rows here and columns, when we look at that multivariate solution here, we're going to have material and labor and numerators and denominators raised to different exponential amounts here, and so forth. So you can see the complexity here. Okay, so now if we go and we solve this matrix here in terms of a determinant, we really got two different things we're going to look at here. When you solve it and you don't put in your exact numbers, you can do it. It comes out to an algebraic solution here. So this algebraic solution, we're going to be working with that as well here to understand our change in volumes and our change in slope. So you can see what's going on here. You're going to have labor in the numerator, material in the denominator, raised to some exponential amounts, and so forth here. Same thing. In this portion, you got material and labor both in the numerator to exponential amounts, and over here, just switch material and labor here, raised to some exponential amounts in your numerator and denominator. Okay, so that would be just our algebraic solution here. And this is important because we can use this here, we can linearize this through a Taylor expansion, and it's going to give us the idea and looking at our change in slopes and volumes and so forth. But had we taken this matrix here that we set up and we put in those solution points here based on our constraint optimization here, we would have come up with a determinant matrix here. Same thing as above here, only it is really solved based on those points we're looking at. And you're going to just come up with a matrix or a block of numbers here. Here's our row by rows and by columns here, a block of numbers. Okay, and then if we've gone in here and we put in and solve this determinant here, just using those numbers that we had up above or calculated for our constraint optimization here, we'd come up with a single number here. It really represents a volume, and that's what we're going to be looking at here. Get an understanding of what a determinant is in terms of volume. So we have this algebraic solution here, then we have our numeric solution here, and then we got it. That all turns into, based on our points that we're looking at, that turns into a single number which represents a volume. Okay, so let's go up and let's start looking at it pictorially here. Okay, so first off, this is our production function here. I'm showing this in blue. And really, we're going to look at 3 different points here. And this, based on that constraint optimization here and under different budget constraints here, we're looking at 3 different points. So what we have here is our gradient path here that these points follow. That's our path of maximum revenue that we would have here. And that's all based on this production function that we have here, revenue minus our cost here. And each of those has a tangent plane here. And that's really like it's really in 3D, but it's a 2D tangent plane. We're really looking at 2 different vectors here. Okay, so that's our production function. Now we can turn our production function into that determinant that we were looking at here, and we can go back and look at that. But see, gradient path here in our production function, a kind of steep increase here, and then as we increase our production in terms of material and labor quantities, then it levels off here. Well, we have sort of the same thing here with our gradient. And I'm showing here equal points. I've got both of these plotted out equally here. So this yellow point here, that's that initial point here in our determinant here, and that matches up with our first point here in our production function. So we'll just follow that down here. We just follow that. You can see a real steep descent here, where you have a real steep ascent here in your production function. In your determinant of that production function, real steep descent, and then it keeps going down and down and down, and then it starts leveling off here. And really this path we're looking at here, that's that gradient path, and I've just matched that up to the production function. So again, we'll be looking at 3 different points. They're all matching up here. But really the point is here, we're looking at the change in slope. And our change in slope is going to be in terms of volume when we talk about determinant here. And I've got a graphed out here, this green a pattern here, or a green pattern with those grid lines in here. That's that multivariate solution here. So let's go down and look at that once more here. Okay, so this is that green surface that I have graphed out here. That is the multivariate solution of the determinant. It isn't exactly self at any point here. It's just the general solution. You can see the complexity here. Okay, so if we go up here and look at it in these terms here. So in this blue line, that's just our gradient line based on the maximum, our optimization line, or our maximum output line here. But nonetheless, you see the change in slope. So that's what change in slope, real steep here, and then it levels off, but it's going down here. And then that just compared again to our production function. Real steep slope here, it levels off here, but it's increasing sort of here, whereas with our determinant, it's going down here. And then if we further move over here, we'll just look at this first point here. Now this is the underside of that determinant I'm showing here. I can't show it on the top side because when we talk about this, we're looking at it in terms of volume here. We talk about a tangent plane, and really it's a 3D volume here. Whereas our production function, we were looking at a 2D plane here. When we talk about a determinant, we're really talking about 3Ds beyond just plotting it out here in 3Ds. And this point I'm showing here, that's that solution point that we looked at, that first solution point. And that, again, fits on the underside of our determinant function. That's that determinant function. And if you look at it in terms of our production function, I've just overlaid them here. So you can see it again here. Our determinant is going down. It's these blue spheres here, and with those 3 different points I'm looking at here. And then each of those points has a tangent plane. Well, it's really a surface tangent plane. It's got like 3 dimensions to it. Now this is where that determinant, it's really looking at the rate of change. We start out with a real steep rate of change decreasing, and then it levels off. And that fits in with our production function as well here. I just got the production function laid underneath it here. Production function's going up here. I'm just showing it here, and then it kind of levels off here. Those tangent planes here. Now with the determinant, you can see it's just the opposite. It starts out here, it's going down, and it levels off here. So that's what we're talking about when we just plot it out in 3D here, this determinant. Okay, so let's go down and let's look at our determinant matrix here. Okay, so when you're talking about this determinant matrix, it's really a 3 by 3, in a matrix, and it has three vectors here. And what we're looking at, and this, everything on this determinant with volume is going to be based off these vectors here. So we got R1, our first vector here, that would be the row here, 0, 200, 350 represented here. This is a 3D space here, these vectors. And that would also be represented by column 1, same thing. You could either use column 1, 0, 200, 350, or row 1, 0, 200, 350. Okay, and then our other two vectors are R2 and R3. R3 actually starts at 0 here, but I couldn't just plot it out. So R2 would be row 2 here, and R3 would be row 3 here. Or you could look at our C2 here and C3 here. So that's our determinant matrix. Either look at it in terms of rows or terms in columns. The columns and rows match up here. But why do this really represents an area that we're looking at. So moving over here, when our area isn't going to be quite this dimensional here, because it's going to be like a flattened out matchbox that we're going to actually be looking at here. But this is what we're talking about, the determinant and the volume. So based on that solution point that we had here, 69 of material, 69 units of material, 78 of labor, fractional amounts, we would have come up with a determinant of volume amount here of 497,300,000. So that's really that change in slope that we're looking at that point. It's in terms of a volume. So if we look at, and when we're talking about determinants, they really, I may pronounce this wrong here, but it's a parallelepiped here. It's really got 6 different faces, 8 vertices here, and it's all based off these vectors here. This R1, again, our determinant we're going to look at is kind of squashed down here, where we got the R3 and R2, or row 3 and row 2 on top of each other essentially. But nonetheless, you can see the matchup here. R1's going up here, and our determinant volume is going here, and then R3 and R2 are down at the bottom here. But nonetheless, you're going to have 3 different vectors you're dealing with when you're talking about this 3x3 determinant here. And building on those vectors here, let's just follow this one up here. R1, well, the back part of our vector, or back part of our determinant, or our parallelepiped here, is R1 plus R3. This top part here, and then this vector point here would be R1 plus R2 plus R3. That is, you'd be adding up those different vectors here that we're looking at, defined by those rows or columns. And then moving over here, R1 plus R2, and so forth, R2 plus R3 back here. But that's what we're going to be working with here. Just to understand the determinant matrix, in this case it's 3x3 matrix, 3 vectors here, and it's really representing the change. In this case, our determinant is based on a Hessian matrix, or a second derivative change at our various points here. But this is just to understand here how we set up this with the determinant matrix. Was sort of a complicated multivariate calculus problem, but when we set in our points here, we come up with a block of numbers essentially here, represented by rows or columns, and then those block of numbers are represented by vectors here, either showing here R1, R2, R3, and so forth, R1, R2, R3, and those vectors here are really they come up with a parallelepiped here when you're talking about the in this case the determinant, a 3x3 determinant here with a multivariate solution. Okay, so that is, we'll move on from here. Now we'll look at this determinant in terms of a 3D space or a volume here at those specific points that we were working with. 69 units of material, 78 units of labor here. And we're going to prove that the determinant value here is equal to the volume of a parallelepiped here. And I'm using MapleSoft here to define this parallelepiped and determine the volume of it. Okay, so what we're doing here is we start with our determinant matrix and look at it in terms of rows and columns. And these are the 3 rows and columns that we would use here for determining our determinant's volume here. So row 1 I'm showing here, row 2 and row 3 here. And it's also interesting to note that column 1 and column 2 and column 3 represent really row 1. So let's look at row 1 here just to understand it. Row 1 is 0, 200, and 350. So that's a point out or a vector in space that we're looking at. And then column 1 would be the same, 0, 200, and 350. Row 2, 200, and then a minus 1.68 here, and then a plus 386. Column 2 would be the same. in this case, it would be 200, 1 minus 1, 683, and then 386. Okay, so you got a 3 by 3 sort of symmetric matrix here. And again, this matrix here represents the volume of that parallelepiped that we initially looked at here, where you have these three vectors here represented by a row or our columns here. Okay, so for our example, this is what we're going to be looking at. So we're going to be going through this determinant matrix in terms of this parallelepiped here, the volume here. So our vectors here in just terms of row 1, row 2, and row 3 with our volume diagram here for a parallelepiped. So row 1 would be represented here by starting, and everything starts at a 0, 0 point here when you're determining the determinants, and in this case the parallelepiped, in order to get the correct volume entry. So you're going to have row 1 is represented by this green vector here moving up here to a point here. So that's our row 1, 0, 200, 350 right here. And then row 2 would be the blue, little blue vector here, starting again at 0 and moving this way. The thing is, with row 2 and row 3, they really lie on top of each other here. So row 3 and row 2, they really have points in common, let's just put it that way. They're a little different, but they have some points in common here. Okay, so row 3 really starts at 0 and moves up here. So that's our determinant matrix that we're looking at, and we're going to convert that into a parallelepiped or a volume here. Okay, so what I've done here, and we'll just go through it. You're dealing with 6 faces and 8 vertices here, and putting it into our computer software or MapleSoft, it's going to spit out the exact vectors here are points for our faces and our vertices. So let's just start with our vectors here, our vertices here. So I've called out the parallelepiped here, putting in our vectors here, R1, R2, and R3, which is either the rows here. It's going to give us these 8 different vertices that we're showing here. I'm showing on the top here, this is the front side, incidentally. You got red, blue, yellow, and green here. And then the bottom, yellow, blue, yellow here, and green here. Okay, so really we got 2 different faces here on this parallelogram here, essentially. And I've got them numbered here, these different faces here. And what we could do here is we could go and look at those faces, because the computer has generated the face, the exact gives us exact dimensions here, or the vertices here for each of those faces, and we can go and look at that as well here. So maybe let's do that right now here. So let's just say we know what our vectors are here. The computer gave us those here. And then to just look at our faces, let's just go and really look at it quickly. Just to understand, we don't have to do it, but let's just understand that this is part of the software that's working. So for face 1 here, which is really this starting out with our yellow dot here, and then blue here, and then blue here, and then red here, it's just moving over here. That would be our parallelogram face here, showing 4 different points here in space. And then the other front surface, I got a 5 here. Well, we can look at that later here. But nonetheless, that's how we're working with it. So if we go down and we look at our second face, and let's move down here. That's going to be down here. And this is really the back side of our parallelogram here. So here was our red arrow here that we had up above. Now we're looking at our vector essentially here. This is the one in our backside. It's over on this side. And then our other vectors here, our blue R2 vector, row 2 vector is shown over here, and then R3 is shown over here. So you can see we're looking into the backside here. We're just trying to make some proofs of this. So let's just look at the backside here. This second parallelogram face here, and that's shown by those 4 dots here, or there's 4 spheres here. And if we went up here, I defined those because I know what they are here because the computer gave them to me here. I said A5 through A8 here. Those are the different lines essentially or points that define that vector or that face 2 here. Okay, so you understand what's going on here. So if we move down over here, let's just move up to our numbers here. So we got parallelogram faces, we got face 1, and just to note here where the zeros are, they start at a 0, 0 point here. So when you put it into the computer, you have to remember to start your origin here at 0, 0, 0, or a 3D space, X, Y, Z, all at 0 here. And then the computer would give me face 2, Face 3, again, it shows where these are all the vertices, or these faces here. So we know that we have 6 different parallelogram faces here. And in face 4, I'm only going through this because this is what the computer, you have to understand what's going on here and how the computer can give you all these numbers here, and how it generates the volume here. And then 5 over here and 6 here. So let's go back to our parallelogram here. So again, let's just start out with face 1 here, defined by those different points here, by our little spheres that I'm showing here. And then we also have I have face 5 that corresponds to those numbers, or those that I have here, those different faces. So the vector points here that we're dealing with for 5, you see, this is where it comes into play, where we got a squashed down parallelogram here. You can see for 5 here, I go from blue, blue, and then it goes over to green, green. But you see the yellow here, those yellow dots? That is the backside, of part of the face of the backside here. So on the front side, I got 2 faces here, face 1 and face 5, defined by my my vector points here. And then face 4 here is really that top edge here. It is so slim here. That's why we got our parallelogram all squashed down here. Okay, so that's looking into the front here. We got our vectors, and we got 2 faces here, plus a face on this top edge, which is really a squashed down face that we're looking at. And then if we go down below here, okay, so this is our backside here. Again, we got our vectors, remember R1, R2, R3 shown here. So this second face, well, let's just look at the second face. It's defined by those 4 points here. Those are our parallelogram faces here. And then the third face is shown over here. But you notice here why it's different than on the other side, that would have been I think the first face here. First face over here. Let's just look at it up here. All right. Here's the third face, the backside. So the first face, really, we're showing a hidden line back here. It would come in from those blue spheres here. And the back face here is a little wider. It's from, you can see it goes from red to yellow to yellow to yellow here. The front face stopped here. So you can see there's a hidden line in here just to prove that there are actually 6 parallelogram faces. And then so we got the second and third face, and then the sixth face is really the edge face. I'm talking about, this is at the bottom, the edge face. So let's go back, and maybe we could look at those a little bit here. So let's look at, in terms of looking into this parallelogram, when we're looking down here on our top edge, and that would be like on here, either front or back, it doesn't matter. But you can see those are our 4 vertices here for our top face. And you can see the yellow one here doesn't pass through on the front side, it's on the underside. So you can see the front side, this is face, this is a face, this is a face here. And so we got a top edge here that is actually a squashed down part of our parallelogram here. So you can see how that works. Just understand 4 points here, but we have 2 faces on each side here. And then that's for face 4, and then our edge face 4 here, and then the bottom edge face, same thing here. You can see what's going on here. Here's our vectors here, and then you can see where that is here, where we got 4 different points here, 4 vertices here. And then this yellow one, that passes through on the bottom, on the back side here. You see it, then it's not going through here. So you've got, again, just 2 faces on each side, and then you got, so that adds up to 4 faces on the sides, or on the looking into the front and back, and then you got 1 face on each here, the bottom edge face and the top edge face. So the key is here, we know that it's a parallel pipe, but we got all our vertices that we were showing here, top, front side, back side, and looking at our edges here, and we know that we've got 6 parallelogram faces, 2 on the front, 2 on the back, plus our edge faces here. Edge faces are pretty hard to see with this particular determinant matrix, because those vectors lie on top of each other. But nonetheless, put it into the computer, and it, based on all our inputs here, 6 parallelogram faces, 8, and the 8 vectors, we're going to get the volume of this parallel pipe that we're looking at is what? 4.973 10 to the 5th, or 497,000 300. And that is exactly what we calculated our determinant to be. Same thing. So we proved that the volume here of our parallelepiped here, or parallelogram, equals the determinant. And then just further to expand on that, let's go back up here. So remember we had that, this is the solution of our matrix. Just looking at that multivariate calculus matrix that we had set up here, this is without putting any numbers to it or any solution points. It's just the value here. So you can see you've got such an algebraic term here, multivariate calculus sort of algebraic term. So if we go in here and we just take those the solution points that we're looking at, x and y, material and labor, and do a Taylor expansion on it, a second degree Taylor expansion, what it does is gives us, linearizes this multivariate calculus solution here. In terms of doing a Taylor expansion, it linearizes that, and it's going to give you some number here, and then it's going to give you x and y coordinates here in a linear solution, certain numbers here, quantities of each of those. And what that's doing here, and then what we do is we put in those points here, 69 and 78, into this Taylor expansion, and it's going to give us the volume here of 497,300, same as our determinant here. And we've done that through the Taylor expansion. We've done it to looking at the parallelepiped, the volume here. So we've proven here that and made a relationship with that determinant, looking at it in terms of our multivariate solution here, where we put in our numbers here and we come up with a linear solution and a linear understanding of it. So let's go and let's look at that linear understanding here. So really, that is nothing more than this tangent surface here. That is the determinant here in 3D space, or the volume here. That's that tangent surface. It's really not a 2D surface, it'd be like a 3D surface, because it has a volume to it here. So that is shown here. So that is our determinant. Here's our determinant function here. It was really this function here, plotted here, and this is a specific point here, this blue point here. This is our tangent, our path, our gradient path that we're following down here, those red spheres here. And lies on it is the determinant here, that volume of 497,300. And we define that here by using a Taylor expansion against the multivariate determined solution that we have here. Okay, so that's it. And then just looking down here, you can see it, how it fits in here. We got those two different vectors here. Actually, there's three vectors here, but just looking at the Taylor expansion, we end up with two vectors here. When we were looking at the parallelepiped, we had three vectors here. And this red one I'm just showing as a directional vector, showing the direction that's going in here. Okay, so we can go and we can further just look at some numbers here and look at all three of those different points that we were looking at when we initially started along our gradient path here, where we had a number in the beginning, a mid-range number, and then a number here. But you can see here with this one here, my determinant that I plotted here, our tangent is on the bottom side here. Our plane, our volume plane, or our tangent plane is on the bottom side. Okay, so we'll continue on. Okay, now we'll just make a comparison on those three different points that we're looking at. So here's our determinant function, and here's that midpoint that we're looking at here, this blue sphere, and this was our gradient path that our determinant is following down, and we're really looking at the change in slope here. Okay, so just expanding on our, remember that multivariate determinant solution here, that complicated one. If we did that Taylor expansion, like I mentioned here, second degree, at two different specific points here, you're going to get a linearization here of a multivariate determinant solution here. And it's going to give you an x and y value and a certain other value here, and that determines the tangent plane here. And then if you put those numbers at that specific point here, 69 and 78 here, fractional amounts, into your Taylor expansion linearized solution, you're going to come up with some number here, a scalar number that actually equals our determinant, 497,300,000 here. So we've taken this multivariate determinant here and we've linearized it into a plane that we can look at here and understand a little better. And that equals whatever our matrix determinant, the solution to our matrix determinant at that specific point. Okay, so just going down here again, you can see our gradient line here, and that is the solution here based on those x and y or m and l values that we'd be looking at. So we've linearized it. We were able to determine the volume here, which is really a number here that equals the volume of our determinant. Okay, so just going back up here, just looking at, let's look at the point here. We had 3 different points. That was this first point here, 6.9, 7.8 here. Do the Taylor expansion at second degree against our solution here, and you're going to come up with a number 7.528 10 to the 6th, and that represents the volume at that point. And you can see how it's pointing down here. Real steep volume going down. Then that was that, and this is our second point, was that mid-range point that we calculated here at 69 and 78. Volume of 4.973 or 497,300 to the 5th. And then our last point here was that one here where we would have had x or m equal to 174, fractional amount y equal to 195. Do a Taylor expansion against our determinant multivariate solution, and you're going to come up with another expansion plane here. Each one of them's got a plane here to x and y terms here, plane. And that was really linearizing our multivariate determinant. So you can see there's some rationale here in our determinant. And in this case, we're going to come up with 1.687 10 to the 5th. Okay, so if we do our 3 comparisons here, you got that first point that we looked at here. This is that determinant against our gradient line here, point 1, point 2, point 3. Point 1 was 7.58, and that was at 6 and 7 units of material and labor, x and y. And then our next point here was at 497,300. And that was 68 and 78, something like that, with material and labor, or x and y. And then the last one here was that point here, x 174, y 195, or material and labor, and that comes up to 168,700 or hundreds, whatever. Let's look at it this way. So I've got them graphed out here in multiples, so you can see how the change in slope based on a change in volume here of our determinant. And we looked at it in really 2 different ways here, either doing a Taylor expansion against that multivariate determinant solution we have, or actually looking at the parallelepiped here, or just looking at the solution itself here when you look at determinants in terms of the matrix. So here we start out with, that's 7.5 here, 10 to the 6th. That's 44 times what our last solution was here at these higher numbers, or where we're leveling off here, increasing our material and labor. So just a comparison here, 44 times here for that first point, that times our last point here, and then 3 times here times in that mid-range point here, 4.973 10 to the 5th, and then we got to 1.687 10 to the 5th here. Okay, so you just see change in slope, change in volume, and that's how the determinant works. And then just looking at our determinant matrix, had we did each of those points here, I'm just showing there is, yes, a different matrix that's used at each one of these points. So for that first point, 6.8, 7 point something here units, this is what you would have got here. You can see the matrix here. Different numbers, rows, columns. We have a 3x3 matrix here. Apt to be the rows and rows, first row, first column is the same between all of these matrices. What does change is that multivariate solution part here, with the m and labor raised to those exponential amounts. So here is that first determinant matrix. Here's our second determinant matrix, 4.973 10 to the 5th here. And then our last determinant matrix with that 174 units and 195 units here, x and y, material and labor. So you can see. So you're really working off, when you're talking about determinant matrices, in this case we've got that 3x3 matrix. You got some numbers here, but then you can apply those numbers and looking at them visually here to see exactly what's going on with the determinant in terms of volumes and directions and so forth. Okay, so that'll end our discussion.